Next, let's look at a very interesting concept called a binomial coefficient and identity. A binomial expression is a sum of two terms, let's say x plus y. And we can use the counting principles to find how many different coefficients are there in expansion of x plus 1, x plus y to the nth power. Here n is a positive integer. Let's look at the simple case. Here n equals 3. So we have x plus 1 to the third power. You can expand it like this way. And then finally you can see this is the x plus y equals 3 equal to this formula right here. We arrange the power of the terms from x to the 3, y to the 0, 3, x to the 2, y, 3, x, y2, plus y to the third. And you can see that this is actually the expansion of x plus y to the third power. And then the question is, so these are the coefficients. So this is the 1, this is the 1. The question is, what if we want to look at for a general n? What will be the coefficient? How to calculate them, their coefficients? The binomial theorem states that for a general n, it can be expand this polynomial into the following term. Okay, so there will be the sum of the terms. Each one of the term will have the x to the n minus j's power times y to the j's power, and also a combination of nj, and you expand them. The polynomial equals to the first term is like this: x to the n times n 0 combination, and next term should be x to the n minus 1 power, y to the first, n to the 1 power combination, and then goes on. So this is the last term, combination n, y to the n. So how can we prove this one? We can use the combinatorial reasoning here, and in terms of the expansion of the x plus 1 to the nth power, here we want to look at the form of the x to the n minus j, y to the j's. And to form this term, it is actually to choose n minus j x from the n sums. Okay, so if you choose the x from the n sums, then the y's term is already determined, because you can see the power of this two term always equals to the n. Okay, so you can only look at the x, and it's like there you're trying to find the combinations of the n, and then take n minus j of the x from the n sums. So this is the combination of n minus j. Okay, and here we use combinations because the order doesn't matter, because this is all x and y's, they're all the same. Okay, so therefore, using the binomial theorem, we can calculate the coefficients of any term inside the binomial expansion. So let's look at this following example. In here, we have the binomial expansion, which is 2x minus 3y to the 25th. And we want to calculate the coefficient of the x to the 12, y to the 13 in it. So here you need to look at, first of all, n is equal to 25. Here, the j is equal to the 13. Okay, so, and then you can use these two numbers to calculate. And don't forget, there are parameters, coefficients on x and y. So this is actually the coefficient for y should be minus 3. So minus 3, don't forget the minus. So here we can look at that using the binomial theorem. The number shall be 25 combination 13, and then y's coefficient shall be a 2 in the coefficient, because this is the x coefficient should be 2 and the power to be 12, and also for y's coefficient is minus 3 and to the 13th. And then this is be the final answer for this example. Permutation and combinations can also have generalized situations. Okay, so here we can look at some cases where the repetition are allowed. That means there can be repeated items inside a set. Okay, so how to calculate their permutation and combination. So here, the number of the R permutations in a set with the repetition allowed is actually very easy. So that is actually n to the r's power. Okay, because when repetition is allowed, then you take each one of positions. You can think of there are positions. Each one of positions is just n. So there are r of them. So that together, that's n to the r's power. Let's look at one example. How many strings of length r can be performed from the uppercase letter of the English alphabet? Okay, so here you can see that we allow the repeatance of letters. So there you can see that you can use the here the n's is equal to 26 and r is here. So therefore the answer is 26 to the r. Let's look at the very interesting concept of the combinations with repetition allowed. We start with the example. You can see that the example is very interesting. How many ways are there to select 5 bills from a box containing at least 5 of each one of the following denominations? They are 1, 2, 5, 10, 20, 50, and 100. So here, please emphasize here that at least 5 of each. You're selecting 5 bills, but each one of the denominations has at least 5 of them. So you can actually select multiple 1s or multiple 2s or multiple 5s. So that's the meaning of the repetitions allowed. And here we don't care about the order. So this is a combination with the repetition. So how can we solve this question? So we can consider that we place the selected bills in the appropriate position of the cache box listed below. Here you can see the boxes are actually divided into different smaller boxes. We have this is the first one, first dollar, $1, $2, $5 denomination. Each one is a separate box. And then let's look at some possible ways of placing the bills. If you are choosing 2 10s and 3 1s, it's like you're put the 3 bills in the rightmost box and then 2 bills in the fourth box here. If you consider the boxes, if there's nothing in it, you can consider there's a bar here, there's another bar here, there's another bar here, and if there are 2 bills here, you can consider this is there are 2 bills here, and there is a bar here, and there are 3 bills here. And then this will be translated to the right simple here. And this is another situation, okay? And can be translated into here, this one. So all the different ways of selecting bill can be correspond to the number of ways to arrange the bars and the stars. And there are 6 bars in this example, 5 bars in this example. So therefore you can calculate the unordered selection of 5 objects from the 11 set of 11. Okay, because you are trying to select 5 of the stars, and from the total position is 6 plus 5 positions. Okay, so that's equal to 11. So therefore, the number should be C11 5. From this example, we can easily see that the R combination from n elements with repetition allowed is equal to the following number, which is equal to Cn plus R minus 1 R combination, or it's also equal to Cn plus R minus 1 and minus 1. So this is actually because using the corollary in the combination, n plus R minus 1 minus R and is equal to n minus 1. Okay, so you can using this one is a number minus r. Okay, so because Cn k is equal to Cn n minus k. So by using this corollary, you can prove this. And by the previous question, so the solution can be calculated as because there are 7 different denominations and you select 5 bills, so n is equal to 7, r equal to 5. So together that's 7 plus 5 minus 1, which is 11. Okay. Next example, using the previous corollary, you can see we can easily calculate the following example. Suppose that a cookie shop has 4 different kinds of cookies. How many different ways can 6 cookies be chosen? So to answer this question, you need to understand which one is n, which one is r. So in this question, there are 4 different kinds of cookies. So n equals 4, and r is how many choice. You choose how many cookies. So r is equal to 6. So then you can use the formula. So that will equal to C n plus r minus 1, and r, which is equal to C 4 plus 6 minus 1, and 6, which is equal to C 9, 6. This is the answer. Okay. And for easy of remembering, we have listed all the permutation combination numbers formula inside table 1. So the first 2 are the permutation not allowed formula, and the last 2 are the permutations are allowed formula inside the table 1 for easy of remembering.